Hello. So one more short video about energy in the Earth system. This was motivated by some questions that people had in the discussion space. In an effort, also, this is motivated by an effort to try to put this into a perspective that will allow us to use this in our future work about weather. This recognizes that this is big scale stuff. There's some big abstractions here and we want to make sure that we're able to connect this to our future learning. So, trying some perspective. A place to start is understanding why we have seasonal variation across the globe, and a common misconception amongst students is that this change in seasonal temperatures and weather and so forth is related to the distance between the Earth and the Sun. Obviously, this is not to scale. In actuality, when you look at the distance values, the Sun is actually closer, or the Sun is actually closer to the Earth in December or January than it is in June. So the real reason that we have seasonal variation is due to this tilt of the Earth's axis, which stays fixed, pointing at the North Star. And as the Earth orbits around the Sun, different parts of the hemisphere are exposed to different angles of light and different duration. So during our summer here in North America, we get a lot of direct rays, okay, that hit the northern hemisphere, and the Sun is up in the sky and pretty high in the sky during the middle of the day. Whereas in our winter here, the northern hemisphere, the direction or the incidence, the angle of the Sun is at a shallower angle, so it's more diffuse, and we don't get as much sunlight during the day. The days are shorter, and the Sun is not so high in the sky. And during the equinoxes, we have equal night and day, and so the impact is the same on both hemispheres. So that's why we. Now back to our evil energy balance diagram. What I hope to do in the next few slides is just to show some applications of this. And the first thing we're going to look at are some maps that show the variation in incoming radiation or incoming solar energy into the system as a function of 2 months. So we're going to look at solar insolation for January 2014. So here's our model for seasons. So we're somewhere in the orbit here. So we're in northern hemisphere winter. And these maps show how much sunlight reached the Earth's surface during the month, average over the month. Okay, a couple of things to notice. One is that because of the tilt, we don't have much incidence or much solar insolation here. Not much sunlight reaches the Earth. It increases as we get to the equator. And at the equator, there is a band of areas that don't get much solar insolation either, and that is because of the consistent cloud cover along these areas. Notice that this is in the southern hemisphere. We're going to see it jump up into the northern hemisphere. And down in the oceans, lots of sunlight because it's summer in the southern hemisphere. Notice that Australia is very bright, as are the Andes. So these are getting a lot of energy, which is measured in watts per meter squared here. So it's an aerial measurement. To June of 2013, we're over here on the orbit, we've had the switch, but notice that that band along the equator is still present. So it's a pretty cloudy area, but we have not much incidence of sun down here, a very high incidence along the desert areas here, Saudi Arabia and Sahara. And that's due to that large global circulation that makes these areas pretty dry. And notice that we have this band up here, which is a band of following the jet stream, which is where we get our summer storms. And notice up in the Pacific Northwest, we have some significant decrease in solar insolation because of clouds. So the next maps show the amount of shortwave radiation that is escaping from the Earth system. So it's these two values here. And these also show the seasonal variation. Here's January 2013. This is reflected short wavelength radiation from the surface. So we're over here on the orbit. Light values are lots of reflection. So things like snow, ice, and clouds reflect a lot of the radiation, some from the surface and some from clouds. Once again, we have that nice prominent band going across here, so this is a pretty consistent pattern. And because of this being winter up here, we have less reflected length, short wavelength radiation because there's not much incoming radiation. The opposite when we go to June. Once again, we're having lots of reflection up in here. Greenland is very reflective because of the snow. And once again, that band is fairly consistent across the equator. So that's the area that gets consistent incoming solar radiation as well as reflected short wavelength radiation. And remember, those the reflected stuff is from either the Earth's surface or clouds in the atmosphere. So the next few slides will show the balance between the incoming radiation and the outgoing radiation. And these slides or these maps are very telling and I think worth looking at. Here is the net radiation for the Earth. This is the balance that we see. Okay. This also is measured in watts per meter squared. The balance point are these light colors, and that once again we'll see this nice distinct pattern going across the equator. The dark areas have a deficit of radiation, and the nice bright areas have a surplus. So as you can look here, hopefully you can guess what season this is. Is this summer? Is this January or June? And hopefully you guessed January because it's summer down here in the southern hemisphere. So here's some definitions right from a website from where I got these maps called NEO, which is NASA Earth Observations. The difference between how much solar energy enters the Earth system and how much heat energy escapes into space is called net radiation. Some places absorb more energy than they give off back to space, so they have an energy surplus. Other places lose more energy to space than they absorb, so they have a deficit. So that's just kind of repeating what I just said. And we can go through that again. Here are balances, here are deficits, here are surpluses. Now some more definitions. Specifically, net radiation is the sum total of short wavelength and long wavelength electromagnetic energy at wavelengths ranging from 0.3 to 100 micrometers that remains in the Earth's system. The net radiation is the energy that's available to influence the climate and weather. On a global scale, the net radiation must be zero, or else the planet's overall temperatures must rise or fall. And so if we're messing with our energy balance, we can influence the climate. So let's take a look at some dates. Here's January, so we're here. We're summer in the southern hemisphere. We have a surplus of radiation or energy here and a deficit, a weak deficit here. And once again, the equator stays pretty balanced, and this is very important, as I'll outline in this section. In March, because we're at the equinox, everybody's getting equal amounts of radiation. The band spreads across the equatorial regions. We have a deficit here in the desert regions. And we once again have this prominent feature across the equator. So it's more, this is definitely more symmetrical. In June, when we're in the summer in the northern hemisphere, once again, here's the equatorial pattern. We have a balance in the Sahara deserts and over here, and in the deserts in China. We have surpluses in the ocean. Here's what's generating the energy for our hurricane seasons. And once again, we have that band of balance up in here around where we have significant mid-latitudinal storms. September, we get the symmetrical pattern, just like we did in March. Go back to this one. And the fundamental, this pattern that we've seen, this fundamentally drives our weather pattern because a lot of energy is locked up year-round in the equatorial regions, and it is the distribution of this energy both north and south of the equatorial regions that help drive our weather. So I hope this puts some perspective on some of the stuff we've been looking at. The main point for our diagram here is that energy is balanced, and that a significant amount of our atmospheric processes are generated by this part of, or this, and then these larger arrows, which are driven by infrared electromagnetic radiation, which is in the form of heat. So that's an important part of this lesson. And the other important part is that this seasonal variation is due to the tilt. So we can connect energy balance with our large scale changes over the year. I hope this helps. Thanks very much.